Hello, my name is Michael, and I first learned how to code in the early 1990s. And during my time working in the software development and engineering industry, I noticed that there has been major shifts over the last couple of decades. There is, in my view, a problem in software development. The problem started, we would say, around the turn of the century when there were major attempts to solve the complexity of writing software, to solve the complexity of dealing with the computer, and to harness the computer as a mechanism to enable productivity, produce software applications, and streamline operations, among other things. So there is, in my view, a problem in software development where we have bloated architectures. We have code that when you write it the standardized way, the way that you are advised to do through books, through articles, through industry conferences, results in more technical debt than we may have had in decades past. So, what is the issue with software development? The issue basically comes down to the stress and, I would say, effort required to masterfully harness the machine. So, the computer, as is classically understood, has a CPU or processor, RAM, and main storage. And part of the objective in software development is to combine these resources together, these hardware resources together, to produce applications that have real world value. For example, the ability to scan product in a retail store, the ability to look up facts and figures about a political figure, the ability to understand your health by having an app that can scan your body and give a good assessment of your health. A huge range of ideas exist that can be implemented using the computer. But when software developers are asked to make this happen, it often occurs through a variety of tools and processes that by this time in 2026, many would deem excessive, and the most common word for that is boilerplate. So the scenario is one where, let's say you have the owner of a company. The owner of the company goes directly to the employees and is able to talk to them directly and get a good idea of how the company is working or not working internally. And that process can be very efficient when you have very few employees. Let's say you got 10, 20 employees. As the owner of the company, you can go directly to the employees and you can make many things happen. But what happens when you have 500 employees? Well, as CEO of the company, it's not so easy to engage with employees. And so you need bureaucracy, you need process, you need all kinds of rules and standards. And that's the same situation we find ourselves with software development in 2026, where you have servers, you have databases, you have microservices, you have all kinds of mechanisms that you want to organize together in order to provide some functionality, provide a service, and optimize a process. So, in order to manage that collection of capabilities, there has developed a set of advice, a set of recommendations that inform the software developer on how to go about putting together these these components in the best way. The issue is that this advice generally sprung from large enterprises as well as what we call the major Silicon Valley companies. And in some way, in a quest for many businesses, smaller IT departments, small startups, to get on the road quicker to having the same capabilities, the same scale and growth as these larger companies and these larger Silicon Valley companies, many thought it was a good idea to imitate them, to do the same things that they do. But unfortunately, what scales up doesn't always scale down. So not everyone that builds a website or builds a mobile app or has a internet facing business or even a B2B, business to business setup is going to have 1 million customers a day. Not everyone that builds software solutions is going to have the type of capacity needs that a large Fortune 500 company has or a large Silicon Valley company has. And so the problem you end up with is the attempt to embrace the big company models and approaches has created unnecessary, what we call technical debt, and a great slowdown in the way that technology is delivered and the pace of innovation. So, in my own view, I see a situation where about 30 years ago or somewhere in that ballpark, we had some really good software development practices that worked for large companies, that worked for large enterprises, but they also worked for individuals. We had a view of software development that some from a large company perspective might call simpler, but from the standpoint of someone who's a solo developer or someone working in a small startup or in a business in which the software solution that you're building is not one that is ever destined to be a Wall Street blockbuster application that has to serve 1 million to 1 billion users a week. So those practices from way back when, I think, has a renewed chance to be employed again today. So one of the things that I looked at was a software development approach that allows you to take a software design, a software idea that you're trying to implement for a process that you want to automate. And how can you build that in a way that is reliable, that is not bloated in terms of using so much RAM and in some cases so much CPU, and how can you build it in a way where it is more streamlined in how it is actually put together. So this is something I've been studying for a number of years, and part of that is I had to unlearn some of the enterprise practices that became second nature to me earlier in the time where I was practicing software in major enterprises. So one of the things that I landed upon was safety critical software development. And safety critical software development you can find under standards such as DO-178C. And DO-178C is a standard that is used in many projects and situations where you're building software for aircraft, for orbital satellites, for space stations that is orbiting the planet Earth, and for fighter jets and drones, you name it. But a standard similar to DO-178C is also used in the automotive industry to govern software that's going into cars, right? The cars that you drive every day. So in both cases, whether it's a plane, whether it's a cruise ship, or a cargo vessel, or a car or truck or SUV that you're driving, in all of those cases, you cannot have software that's going to cause the vehicle to have issues, to have accidents. So there were meticulous standards that were developed that informed the software practitioner on the best practices to implement the software to minimize and in some cases eliminate error, to eliminate surprises. And it's the same software practices that allows us to send a rover millions of miles to Mars without any physical service from a technician. And those rovers can run for years unattended. So I thought to myself, that is a good idea. And what if that was applied to our everyday web applications, our mobile apps, and desktop programs? What if? I mean, if it's good enough for high reliability aerospace and fighter jets and lunar landing equipment, then why can't it be good enough for our ordinary software? The answer to that question, right, is that it takes too long to build software that way. It takes too long to build software that way, and it is more expensive. Not expensive in terms of tools, expensive in terms of talent and people. So that is the fundamental reason why we have a different class of software in terms of quality when it comes to our mobile apps, our desktop programs, our websites, and our other systems versus other types of software you don't hear anything about. You don't hear anything about them because there's no controversy associated with them, right? Planes fly every day and they got computer software in them. Boats are sailing on the high seas and there is no news reports that come out that says the software system in those vehicles had an issue. And if there is, it does make major news. And so the fact that we don't hear about it every day is a indication of the level of quality and care that has gone into building the technology for those particular situations. And we have the opposite situation when it comes to our mobile apps. It's so common that we don't even notice it anymore. But every few days you get a software update. Now imagine this. For orbital satellites and for aircraft, for commercial jets, for cruise ships, for cargo ships, for all those types of vehicles that I mentioned earlier, you're not getting software updates every other day or once a week or even once a month. Maybe once a quarter, maybe once a year. In some cases, never, because it's not necessary. And so the frequency of updates on your phone and your tablets and your desktop computers is the clearest indication that there are what you would call continuous issues with the software that has been delivered, that has been designed and defined. So anyone listening to this would be like, okay, well, what do you do about that? So when it comes to companies and how they write software and how they have software instituted to automate a process, that's none of our business. But if you're building software yourself, you do have an opportunity to adopt a different practice. So I wouldn't say any of this if I didn't think that there was a practical and straightforward means to actually pull this off in 2026. So I started this journey in 2012, right? This shift that I'm talking about. And, one of the things that I could tell people back then and up to a few years ago was, well, if you looked at my code and you liked my code, the way that I wrote it, how streamlined and simplified it is, and the time and care that I put into it, the code that I have online on GitHub, you might be inclined to say, well, how do I write software like that? What books could I read? I would point you to books by, let me see if I got her name right, Leanna Reardon, I think that's her name. She has a good book on safety critical software development. And there are other books like that. There's like 10, 12 books that you can buy that cover that, and they are up to date. But, recommending books, can be a tall order, right? When you're looking for a more straightforward solution. So, here's the thing. Many software developers that I hear about, right? Many software developers that I hear about say that the tools that we have today in the form of AI are causing us to produce worse software. These tools, they pattern match, and they are able to gather the aggregate of the average code on the internet that they've been trained on. So you have to ask yourself, what is the average code? The average code has the very patterns that I talked about earlier. They have these enterprise patterns. Even simple software, to-do list, might have a range of enterprise patterns, boilerplate. And so if you ask the AI to vibe code you a to-do application, a slick, souped up to-do application, one that has all the best practices, well, the AI's knowledge base of best practice is going to be Fortune 500. But as we have established, Fortune 500 does not equate to quality. It does not equate to software that is efficient, that uses memory properly, that uses CPU properly. There are some great examples of that on GitHub and through conference presentations that I've seen. But again, that does not represent the majority of code sampled by AI. So the reason why software is getting worse, we just answered our question from earlier. The reason software is getting worse is because software was already bad before AI even showed up on the scene. Since we have so many examples of software that was well-intentioned in terms of how it was built, that doesn't mean that the programmers that put it together were bad programmers. Not at all. And it does not mean that the practices that they have used and continue to use are bad on their own merits, right? In isolation, many of these ideas are good ideas. Some of them came from think tanks. They came out of university and university research. They came from a number of directions, and they were designed overall to solve the problem of complexity and leverage. What does leverage mean? Leverage means that if I can do in one line of code what used to take me 20 lines of code to write, then I'm going to choose the one line of code. It gives me more leverage over the computer. The problem is I have no auditability into that one line of code. Whoever gave me that one line of code, right? whoever gave me that one line of code in the form of an API, an SDK, or a library, or a component, right? We are trusting them to have made the best decisions in the construction of that component. That in and of itself is not a bad idea. The bad idea comes in the combination of different components from different sources and even from the same source. Because when the different components are combined together, when they are compiled into actual code, they all get flattened out into machine code. And the machine codes, they don't always play well together when it comes to performance, when it comes to reliability, when it comes to predictability. And that's why many of these component systems and many of these practices are not used or suggested in the creation of safety critical software. So that is the situation with both AI and with software development as a practice. AI simply makes it more obvious what was going on when we didn't have the AI. And so the thing of it is that there is a good point about having to write 1,000 lines of code over and over again when you can just call a single function that does the same thing. There's a good point about that. Absolutely. Okay. And so in the absence of AI, it did make economical sense to use these more compressed libraries, these more consolidated code tools to streamline the process of engineering software by manual typing, fundamentally manual typing. But here's the thing. Object relational mapping tools such as Entity Framework and even Dapper, object relational management tools such as Hibernate and others, right? Dependency injection, right? Those tools actually save on the typing and simplifies the way the code looks, right? So you can read it at a glance, but they have trade-offs. They do diminish performance. They do increase the amount of technical debt. They do impact software overall in negative ways, and that has become borne out the more we've tried to scale software, even at the Fortune 500 level and in the Silicon Valley level. Some of these ideas, when you get into the weeds of how do they make the software application gain more performance, handle more users, you will find when you dig in the details, they peel back some of these high-level layers, right? They peel these layers. Actually, we have a word for this type of architecture where you have all this layer. It's called the onion architecture. And so the onion architecture reigns supreme in today's software development practice. Now, we have established that, yes, there is a cost to building software better, but we also have a solution to that now. Some may not want to hear this, but it's absolutely true. If AI can generate code in seconds that would take you hours to write yourself, and we're talking about more intricate code, higher performance code that has more depth to it, right? Then the economics of writing that more intricate code has diminished. Now, I say that knowing full well people will point out all kinds of issues with using AI for that. And that's the real reason why I'm talking to you today. Because I have formulated an approach that actually takes this concept of 1990s and early 2000s software development practices that were more rigorous and that produced better performing code that was more respectful of memory, and bring it back into action to build today's software. And here's the good part about that. I have developed an entire software development system that I've proven out and that has the mathematical rigor. I'm not a mathematician, I'm not all of that, but I understand the principles, and I've been able to encode them into AI in such a way where I can produce highly reliable code. I shouldn't say highly reliable, I should say perfect code. Code that's perfect in the sense that it can be analyzed, pattern evaluated from multiple angles to ascertain the quality on the basis of telemetry. So, I said a lot of things there. Let's unpack just a few of those. Let's start with telemetry. In the practice that I'm using, which is inspired by safety critical software development, I'm using telemetry instead of test-driven development. So the conventional practice with software development today, in order to evaluate it, judge its quality during development, and to make assertions as to its fitness to the requirements, hinges on a practice called test-driven development. Test-driven development has the weakness of creating mocks. In many cases, these mocks are done through dependency injection. And in many cases, you are using fake databases, fake data sources, and fabricated inputs in isolated classes and components that can pass a test and show green on the test, but when you actually deploy it to the real world, it still fails when the real world dependencies and components are brought into action. So then when you get an actual database, there's some interactions between a code and a database that causes a crash, or that causes the data to still go in incorrectly. That still causes you to have some cybersecurity issue. There is a better practice, which was born out in an earlier time that is still relevant today. And that is, you simply write a CLI application, a command line application that exercises the components of the software application. The CLI applications in and of themselves become useful utilities by way of reusing these components. And by running these CLI applications, you're able to get a very quick visual trace of the quality and the reliability of the software component in question. If you're building a GUI application, you can have a series of CLI test harnesses on different components that's used by the GUI application in a way where you actually have an alternative to the GUI application, where you can exercise the components with greater rigor and greater iteration than you would either manually clicking through different buttons in the UI or using a screen automation to do the clicking for you. Now, screen automations that do clicking, I think that's a good practice, as is manually testing the GUI, but exercising the components through a actual test harness is going to give you the most in-depth information about the state of those components. And then once you solidify those components, you've built a reliable and trustworthy subsystem that the GUI application can depend on, whether it's a desktop GUI or a web GUI or a mobile app GUI, right? So that is first and foremost the testing methodology that works well with this overall software development methodology that I'm describing. The other thing about it is black box verification, right? So, for example, you have an ETL process where you're transforming data from one source to another, and the source or the destination database or file or whatever you want to call it, it needs to have certain traits and qualities to it in order to indicate that the data was ingested correctly. Now, I say it that way because some processes where you are ingesting data, you're going to produce an outcome where you have accumulated a gigabyte, a couple of gigabytes of data. You're not going to upload that data to a AI. So it can help you there. Your tokens are done even with 300,000 records. So you're not going to verify through the AI, and you're not going to verify through test-driven development. So what you're doing instead is you're running SQL queries. You are generating what's called profilers against the data itself, and you're generating actual counts of the records. You're generating you're pulling out key metadata across the span of records, whether it's in a database or it's in a different data source, right? And you are using a minimized trace pattern of that to have the AI evaluate that, right? You can evaluate it yourself. You can look at it and say, oh, something's off here, right? And then when you combine that with AI, then it can actually recursively evaluate the process it took to generate the error in the first place to actually correct the earlier mistake and produce a better iteration. And so when you do it that way, you end up with far fewer conversational turns with the AI to generate quality code, right? Through telemetry, through black box verification. And so the other aspect of this is going to be the actual definition of the application itself. And for that, there is a set of practices that I would like to show you. So that's going to come in another video, but suffice it to say, what I've developed is a way to systematically develop software that has the same general reliability and quality characteristics as the highest grade software developed for aerospace, automotive, and the like. And the icing on the cake is I also have a parallel process that can take that code that's been developed, executed, tested, and verified, and transform it into a much more conventional software design in terms of how the code is shaped, so that you then bring back readability after you have achieved perfect verification of the implementation. So I call this process Codex Sysytematica. And until you can see my follow-up video on the details of Codex Sysytematica, I will leave links to the article I wrote yesterday in the description and in the comments for anyone who would like to explore it. But until I follow up on this topic, I will see you on the next one.